Yes, sir. Let's start the second session.
Yeah, sure, sir. Yes, sir.
Yeah.
So welcome back, everyone. In the previous session, we discussed about how to develop the Verilog or VHDL code with the Quartus Prime design software and perform functional simulation, the RTL simulation. Now, in this section, we'll understand about the process of synthesis and implementation, and how are we going to use the remote lab to access the FPGA boards, that is virtual labs with remote console. How do we perform the labs, and how do we go ahead with the logics that I'll explain that to you. Right, in the Quartus Prime design software environment, we can see that you have the project navigator, and then you have the tasks window, and then we have the tool view window, and then messages window, and then you have the IP catalog. I explained all of them. That means we have taken an example and then we have gone through that in detail. This is our main toolbar. Here you can see there is a file control where there are dynamic menus, and then we have pin planner, we have chip planner, and then we have compilation controls, compilation report, and then we will discuss more about this platform designer and IP catalog in tomorrow's session. But we will get an idea of how do we use these shortcuts, right? That we will get an idea. Yeah. Right, so let us explore the other portions right now. Right, let us go through that. Now, if you see the tasks window, you can see assignments where we can perform device settings, pin planner, and then we can perform the compilation process, and then we can perform all the three schematics like RTL schematic, then technology schematic, which is after synthesis, and then also after placement and routing, which is the filter operation. Right, now let us explore the details. So first thing is like what we did is called as the new project wizard. That's what we did. When we do a new project wizard, we have the Quartus primary settings file, which is the prime software settings file, which is the QSF, Quartus settings file. We are going to create a new project wizard. So how did we start the project? If you could recollect, we new project wizard, and then we click the new Quartus Prime project, where whether you can use the VHDL or Verilog or system Verilog. So I started with directory name. I provided the C drive, and then what is the name of the project which we provided? We provided add underscore gate and all those things, right? So that we provided. This is for the new project wizard. So in the new project wizard, you can click the empty project, where we can create new project by specifying the project files and libraries, target device family and device, and then Ide tool settings. So all those things we have provided. Then you can recollect this. We need to provide add files option. So since we are going to create a new file, we can skip. I mentioned so that you can directly enter into the next section. In the next device selection, you could see there is the family device which you need to provide, and then you can also provide the filter details, which is the name filter. So as you could recollect, we provided the Max 10 device here, and then M50 DAF484C70. I provided the family filter which we downloaded from the DE10 Lite user manual. So after providing this, the EDA tool settings option, if you want, we can set the model sim Intel FPGA starter edition for performing simulation at this junction. You can specify like this. If you are not specifying this, we can do that while performing simulation. That's what we did during the flow. We have set the model sim Intel FPGA starter edition path, and then we configured the test bench and performed the RTL simulation. Right, so all these things could be possible. The next thing what we are going to see is called opening an existing project. For example, if you open the Quartus Prime design software here, when we close this project, okay, I will open this again, right? So just at this junction, just we'll close this project, which is the logic gate design. Okay? You can see open an existing project. When you say, you can see all these projects are the recent projects. You can open any of these projects. For example, when I click this and get.qpf, so you can click this project. So this project is the project which is already created. we can directly open this project. You can see that. Right, and then we can perform compilation, whatever steps we wanted to. Right. So we can close this project. And then we have opened the logic gate design project, which is the project which we created right now, is the second project. You can see that. I can click that project. Now we have opened our project. This is the way how you can open an existing project. So the existing project will be having the QPF extension, which is called as the Quartus project file. If you close this project, you can see that SoC system.qpf. You can see signal tap demo.qpf, and you can see andgate.qpf. So all these things are Quartus project file. It is our responsibility to open the QPF file in order to open an existing project. So this is the way how we open an existing project. That's what is mentioned in the slide also. You can click an open project, or you can also say from the recent project. So otherwise, you can directly go to the open project and then you can open the QPF file, which is the Quartus project file that could be opened from anywhere where you kept in your directory. Right. So these are the options that are available. Right. Now let us move on to the flow, and then we will do the steps one by one. Okay. So let me walk you through the compilation flow. Right. So what is the first step we are going to do here? We are going to perform the design files. That means you have the Verilog or the VHDL code. We need to perform analysis and elaboration first. That's what we did. When we opened the Verilog or VHDL code, first we checked for the syntax and semantics, which is called as the analysis and elaboration. After we performed analysis and elaboration, we developed a test bench, and then we performed functional simulation. So till this specific step we have done. What we have done so far is we performed analysis and elaboration. Then we performed functional simulation. What we are supposed to do right now, we need to apply constraints and settings. There are two kinds of constraints. One is called as the pin constraints, which we need to provide. The other one is called as the timing constraints, which we need to provide the timing constraints for the design. It can be clock constraints, it can be IO constraints, or it can be a timing exceptions like false paths, multi-cycle paths, or whatever, which we will discuss in detail later. Now you could see that we perform the synthesis process, and then we need to perform the fitter process. So the fitter process is called as the placement and routing. We need to perform placement and routing, and then we generate the programming file. This programming file is called as the SRAM object file, which we are generating. So first we will do, right, we will perform this in the traditional method and generate the SRAM object file, and we will implement the design onto the FPGA board. The second step is, since we don't have the FPGA board with us, we can access that through the remote console, which we call that as the virtual labs with the remote console. So we are going to do that. So I'm going to show you a demo and share the lab files with you so that you can also practice and implement on the virtual lab. So that is definitely possible. Right. So what is the step we have to do right now? It's like we need to apply the constraints, and then we need to perform synthesis, and then we need to perform fit, which is called as the placement and routing operation. So let us explore what is happening on the synthesis stage, what is happening on the fitter stage, placement and routing, and then we will go back and do those steps in the design. What is synthesis? What is fitter? Let us explore that right now. So in the synthesis process, we are translating HDL source files into an Atom netlist. That means it can be a Verilog code, or it can be a VHDL code, or it can be any third-party logic. So we take that code and then we perform the synthesis process where it is getting converted to logic cells, right? That means I explained you about the lookup tables and then the adaptive logic modules, and then registers, flip-flops, and then IOs, RAM, which is your memory resources, DSP, which is your digital signal processing resource, which is your dedicated multiplier and accumulative unit. So all those things would be taken. So now from the design, we will come to know that how many lookup tables it has taken, how many memory blocks it has taken, and how many digital signal processing blocks it has taken. So all those things we can see in the resource usage summary. So that could be known to us. Right. What is the next important thing we need to know about is the fitter operation. So this is after post synthesis, right? Now what happens when we do placement and routing, which is called the fitter operation when you say. So the fitter is the advanced placement and routing engine. Okay, so this advanced placement and routing engine, the fitter, consists of 4 stages. One is the plan. Second one is called early place, then place, and then route. These are the 4 steps that we need to do. Now, what is very important for us is like, what is the time consuming stage when you say in an FPGA design? The placement and routing is the time consuming stage. So in order to perform placement and routing, if it takes more number of hours, and then finally, if the design is not meeting timing, it is a challenge for us. So why can't you split that into multiple parts and then do this operation when you say? That is the greatest idea of performing this. You can see that it consists of 4 stages, but the stages can be run right all at the same time, or they can be run individually. What is the advantage of running them individually when you say? When the design is meeting timing or we are happy with the reports, then we could continue to the next step. When we are not happy with the reports, there is no point in continuing further. We can go back to synthesis stage once again. So what is the basic idea here is the stages can be run all at the same time or it can be run individually. But we have to ensure that the prior stages must be complete before running the later stages. We have to ensure that we have to complete the previous stages before we go to the next stage. That means we have to complete placement, then only we should go to routing. We cannot directly do routing. Okay? Right. So what do we call this? We call this as a snapshot. The output of each stage is a database and it is referred as a snapshot. And this is useful for incremental optimization. And we ensure that we are optimizing the design at each checkpoint. So we ensure that we use this at each checkpoint, and that will be helpful for us. So remember 2 things. One is called as the snapshot, and then we need to understand there is the checkpoint. So now only when the early place and the place is fine, then only we can go for routing. Otherwise, there is no need to do routing. That is the base idea. So this is useful for us to perform the placement and routing operation, the fitting operations for large complex designs, because we are very much sure then we can continue with the next step. If the design is not meeting timing or if there is timing critical, there is no point in proceeding further. We can go back and then fine tune the design and then we can do the next step. Okay. Let us explore this now. So we'll go back to the Quartus Prime Design software, the design files which we have already designed. So let us explore the analysis and elaboration. Okay, so let us do that first.
Padmanaban sir,
Yes, sir.
just one query. When you open that project once again, you have both the test bench and the main file there, Verilog file.
Right.
But I am not getting the test bench there.
Right. So yours would be having the hierarchy. You can go to the files so that you can see.
Okay. Okay. Thank you. I got it.
Yeah. So now what we are supposed to do, like we have done analysis and the synthesis, that means we have done the elaboration so far. What we are going to do right now is like we are going to perform synthesis. And then before we do placement and routing, we can also do pin planning. Right. So pin planning is something which is very important for us to do. Right. How do we do that pin planning and how do we approach this pin planning for this design, that is applying the pin constraints? So let us explore that here. I have asked you to download the DE10 Lite user manual, right? So you can see that in the DE10 Lite user manual, you can refer the details related to LEDs, switches, as well as the hexadecimal displays. In our design, what is very important for us is like we have 2 inputs and then we have 1 output. So the two inputs you can take it as switches, and one output you can take it as an LED. So we can check the pin details here. So where they are available, that we can explore it from here. Okay. So you can scroll through the DE10 Lite lab manual, where you need to get the details of the switches. For example, the page number 26, if you go, these are the 10 switches you have, SW0, SW9. And the pin numbers are provided here. And then the IO standard, right? The voltage that is also provided, 3.3 volt LVTTL. We require only two switches for this design because it's an AND gate. And we require two switches, like we take A and B as two switches. And for Y, we can take an LED. We require only one LED. There are 10 LEDs that are available. What is important for us is to provide the pin details. That is the FPGA pin details here. So how do we go ahead? Like, let us explore that here. Okay, you can do till compilation and generating the SRAM object file. So till those steps are common for everyone, you can do that. Only the implementation on the board, I will do it traditionally with the board what I have. But in the second demo, I'm going to show you how that could be done virtually. Right after the demo is shown to you, you can also try that virtual labs with the remote console, where you can connect to the board, okay, and then check the functionality. Right, let us explore this right now. What is important for us is like there are two switches, SW0, SW1. You can see pin underscore C10 and pin underscore C11. And then 3.3 volt LVTTL is there. So now we can go to the Quartus Prime Design software. And then you can go to the assignments. And then we can click pin planner. Assignments, pin planner. Click that. Now, when you see the pin planner here, it shows A, B, Y. And the direction it shows A input, B input, Y output. But you can see the location is blank. That means we should provide the location, and then we are going to provide the IO stand. Okay, right. From the manual, we are very clear that what is the pin number. So pin underscore C10 and the pin underscore C11. These two I can take for switches. And the pin underscore A8 that I can take it for the LED. So this we can specify in the pin plan. What we can do right now. So pin underscore C10. Okay. And then what is important here is the IO standard. So if you go through that, there is a 3.3 volt LVTTL is there that you can prove. And the other one is pin underscore C11. This is what is provided. And for that, you could see again the IO standard is 3.3 volt LVTTL. And then for Y, you can again refer it as I mentioned, it is pin underscore A8. Okay, so that is for the LED. This is for the Y. So you can provide here pin underscore A8. Okay, and then what you can also provide is like 3.3 volt LVTT. Now we have provided all these details here. Pin underscore C10, pin underscore C11, and pin underscore A8 that we have provided. Right? So you could see that by selecting this, right, you could see what are the inputs and outputs that which we have provided is also available here, right? We can see which bank it is available also. Right, we can minimize this right now. And we can perform synthesis right now. So you could see right here, analysis and synthesis. You can right click and say start. So what I have done, first section, we did only simulation. Now in this section, we are performing pin planning. After performing pin planning, we are performing the synthesis stage. Okay, what happens during synthesis? Let us explore that here. In the earlier case, if you have seen, everything was not showing, right? But here now you can see total number of logic elements, how many, total number of registers, total number of pins, and then you can see memory bits, embedded multiplier, 9-bit elements. You can see the total PLL. That means the phase lock loops for the clocking resources. All those things, how many are utilized, you can see that here. Where we can get the details when you say, Once the design gets synthesized, you can click here, analysis and synthesis, and then you can go to the resource usage summary tab here. If you click that, it clearly shows that how many logic elements are used, total number of combinatorial functions, 4 input functions, logic elements by node, registers, all those things it is shown. So we can get this information. Along with that, what is important during synthesis is like we can see the post-synthesis schematic, right? Which is our mapped schematic. How we can achieve that? Go to the netlist viewers, and then you can go to the technology map viewer post mapping. You can click. So now you can see there is a logic cell. This is your LUT, which is used for this particular design. Now, what we have done so far is only synthesis. We have not performed implementation. So how do we perform implementation? Is like we have to do placement and routing. So we can do all the compilation steps at one stage, or we can also do them step by step, one by one. If you see here, you could see fit, and it shows that placement and routing. Placement and routing is a fitter operation, which we can enable it separate. For example, I can just right click and say start. Now it can show that Quartus prime fitter was successful. What was the difference you could see? At the synthesis stage, it showed how many were utilized, but then how many were available. In that, how many were utilized was not there. That you can see after the filter operation. You can see that it shows the total number of logic elements are utilized 2 out of 49,760. What is the percentage of utilization? You can see total number of pins, total number of virtual pins, and memory bits, all those things you could see that. There are 4 PLLs that are available with the backend device. Out of that, how many are used? It is showing, right? Because it's a pure combo logic. You could see none of the PLL is utilized. All these informations you could see at the end of the filter stage. Now, when we do all these steps at a stretch, when you say yes, there is a compilation tab. So when we say start compilation, it will perform all this process at one step. Okay. So where is this compilation tab? You can see that that's the play button here. When you say start compilation, it performs your analysis and elaboration. It performs synthesis as well as it performs filter, which is placement and routing. We can do that right now. So on the left hand side, you can see that what are the tasks, and on the right hand side, what is the time taken for completion of those tasks will also be seen. And then you can see there is a green tick mark, which you can see that okay, all these processes are completed successfully. Now you can see that it shows all these operations like filter, assembler, which is your programming file. The SRAM object file is generated. We are going to implement the design onto the board right now. Now we have to ensure that all these processes are completely performed before we implement the design onto the board. Right now, where is this our SRAM object file, that is your FPGA implementation file that would be present in your directory. For example, if you go to the logic design which we have generated, right? So that particular file, right? So there you can see, like here, if you open it, so inside the output underscore files folder, you can see there is an and get.sof. This is your programming file, which is called as an SRAM object file, which is generated. All right. So now what we have done so far is we have designed the logic. That means we have performed a fitter operation and generated the SRAM object file. Now we need to implement the design onto the board. So how that could be possible, I will show you. Traditionally, that means I have the board with me, I will show that. But then how we are going to do that virtually that I will show you in the next section, which is the remote lab structure, which could be possible. Right. Now, let me connect the DE10 Lite board with my laptop, and then we can see what is the progress in the implementation logic. So I have connected that board right now. Now we can go to the tools, and then we can go to the programmer. We can see here tools and then programmer. So here you can see when we view tools and then programmer, where you can see this is the device, like 10M50DAF484. This is the device. And which is the SRAM object file is it is taking the output files where it takes the and_gate.sof, which is the SRAM object file. And what is the device name that you can see here? And then whether it is ready to configure, you can see program/configure, it shows a tick. Right. So now what we are supposed to do is we should say start, and then we should see whether it is progressing and shows 100% or not. If it shows 100%, then the programming is successful. Then you can modify the switches, and then you can see whether the LED is glowing or not as per the AND gate functionality. So let us try that right now. So I say start now. It showed failed, right? So let's do one more time. Now you can see it showing 100% successful. Now what we are supposed to do is like we can have two switches, like we used SW0 and SW1, and then we need to use the LED, right, for the output. So now what we can do in the board, we can modify two switches, SW0 and SW1, and then we can check the functionality. That means you can see whether LED 0 is glowing or not as per the AND gate functionality. So that is the traditional method of implementing the design onto the board. Right. So what is the difference when you say we have implemented the design onto the board? When you have the board with us, like physically when you have the board, then it is easy for us to program directly. If that is not the case, then how are we going to proceed to the next step? That's what I'm going to show you. We call that as a remote console, which is called as the virtual labs with the remote console logic. Any questions you have in the traditional flow before we start? Any questions are there, sir, in the chat, or anyone is interested to ask questions? So please unmute and ask before we enter into the remote console session.
Yeah, I have given permission to unmute themselves now. If they have any question, they can ask either by unmuting themselves or using chat window. Yeah, fine, sir. Do you have any questions in this flow till now? Let me know. Otherwise, I'll walk you through the remote console lab. Fine, sir. I hope there are no questions from their side. Let me walk through the remote console lab and then share the manual with them so that they can get hands-on with the remote console with virtual labs. Yes, sir. You can go ahead. Yeah. Sure, sir. Yeah. I will close this right now because I have programmed the design. Now we can close this project also, and then we will try to open a new project. So we can close the main window so that everything will be closed. We are right now in the fit stage, and then we implemented the design. Right. Now, what is the next important step which we need to go through? Is called as the remote console. Right. So I will explain that to you right now, and then we will enter into the details. So in the remote lab, what exactly we are trying to do, I will show that to you. So let me walk you through the GitHub site. Can you just copy paste that link in the chat window? Yeah, sure, sir. This is not required at this junction because just to show what environment we have. The lab manual has everything. So I will just walk you through that. Yeah, this is just the link, but lab manual has everything. Yes, sir.
So here you can see the dev kits. This is for DE10 Lite and DE1 SoC as well as for DE115, where you can use them and access them remotely. Right, what is the process that I will explain to you? Because when you download, you will have all these things here. So this is the zip file, which I will share it with you. If you download that zip file, you have the introduction to remote board, that is the lapsland.pdf file is there, which you could see here. If you see this here, this is our remote lab. This is a remote hands-free lapsland, which we are going to learn today. It is the traditional step, which is till the implementation, we are going to follow the same steps. But when you are going to implement the design onto the board, then we are going to use a different methodology. So how that is followed, I will explain that to you. So what we are going to do is the Lapsland setup. So Lapsland is a company where they have hosted the FPGA kits. We are going to create an username and password and access the FPGA kits for our lab. That's the base idea. You would be given 3 minutes of time where you can have the SRAM object file ready, and we can upload the SRAM object file in order to check the functionality of the design. So that is our main objective. So traditionally, we will generate the design in Quartus Prime design software till implementation and generate the SRAM object file till the steps are same. But while implementing the design onto the board, we will enter into the Lapsland set. So what we need to do, how do we progress that? I will explain this demonstration right now. I will walk you through the lab manual, and then I will implement the design and then show you, so that the same could be done by you also, right? This also requires the Intel Quartus Lite edition. You don't require any other specific things that need to be downloaded. Only the Intel Quartus Prime Design Software Lite Edition 18.0 is sufficient to do this lab. Okay, so let us start with this design. So what is exactly available? I will walk you through that and then we will get into the details. Either you can have the 18.0 or 18.1. Any version is fine. That please ensure that you have that in your PC. And what we are going to do is, like, if you have not downloaded, you can refer the steps here. You can download the Quartus Prime Design software. Especially for this lab, you don't require model sim because our intention is not to perform simulation. Our intention is to implement the design onto the board. Therefore, if required, then you can install model sim, otherwise not required. Since we have already installed model sim, then there is no point, right? You can have the model sim, but in this particular lab, our focus is only on the implementation portion. And for this particular lab, we require the Cyclone 5 device support, where we are going to use the DE1 SoC board. Right, which lab manual need to be downloaded? I will show that to you, and then we'll go ahead and do the process right now. So the lab manual means which we need to download. So I'll just close this content so that we'll get an idea of what is available here. All right, so now what we can do is, like, I can close this content. So I can say DE1 SoC lab manual. If you click this will take you to the page where you can download the lab manual. You can just type that in the Google page, you will get that, the first one, DE1 SoC user manual. That is sufficient. So let it open. I will show you what exactly is the difference between the Max 10 and Cyclone 5 device flow. So this is available in the Terasic website, who is our partner, where you can get more details about the other boards also. But since our training is focused on only Max 10 and Cyclone 5, we will have discussions on DE10 Lite as well as DE1 SoC. Okay, not on other things. Okay, let me open it right now. If you open the user manual here, the DE1 SoC, right, which is why DE1 SoC, because our interest is to understand the system on chip SoC for tomorrow's and for Saturday's class. So I have taken DE1 SoC as a platform. Today we will just use it as an FPGA, and tomorrow and day after tomorrow we will use them as a system on chip. We can use an SoC, like we can see how we can integrate the FPGA along with the hard processor system. Okay, right. So what is the difference? Here we need to ensure that whether we have the correct family details. Okay, so how do we know that? You can see the DE1 SoC. You can see you have the FPGA section as well as you have the processor section. Both are available. So you have the FPGA plus HPS. So the SoC FPGA is one which has both the FPGA as well as the hard processor system section, which is having the dual core ARM Cortex A9. But let us explore only the FPGA section today and implement the design onto the board. The other detail, like what is an SoC FPGA, we will discuss in detail in the tomorrow's class. Right, let us explore. If you see this FPGA, right, you can see the HPS, the hard processor system, is also embedded in the FPGA fabric. But on the FPGA side, if you see, we have hexadecimal displays, we have switches, and then we have LEDs. This is what we are going to use for our lab. Okay, we are going to use this right now. And what is the family device? When you say this is ICSEMA5 31 device. So this is the device which we are going to use. Right, you don't require the Cyclone 5 SoC device with you right now, because we are going to use the labs LAN setup where we use the virtual labs with remote console. What is only important thing we should require is to copy this family filter and then copy paste it into your directory when you are creating the lab for it. Okay, the same is also copied in the lab manual. If you don't have, you have not downloaded the DE1 SoC lab manual also, it is specified in the lab manual. You can see that. What is the corresponding device? That information is also provided. This is the device which you are going to use. Okay, it is available in both places, but what I wanted to show to you is like you will get an idea of which is the DE1 SoC and how do we do that with the virtual. So let me walk you through the lab map so that I will share it with you so that you can follow the same steps. Right, now you can see there is a new project wizard where we are going to create it. So let us close the open the Quartus Prime Design software and then continue the lab right now. So we have to create a new project wizard. And then you can say here, switch to LED demo, something like that you take. Please ensure that the name of the project should be switch to LED. That's what is provided. So please follow the same. Okay, switch _to _LED. And it is case sensitive. Please follow the same. So here we should take switch _ to _LED. Okay, so what is the name of this project? Is switch _ to _LED. And what is the name of the top level entity? That is also provided. So you say next here, like the earlier design. Empty project, because we are going to copy paste and create the design. Then next, add files. We are going to create it. So next, right here we have to be very, very careful, because in the earlier case, what we did was in the family device and board settings. Last time we created with a Max 10 device. Now we need to do that with a Cyclone 5. So Cyclone 5 it is selected, but then family filter we have to copy paste and then select the corresponding device, because the FPGA which are hosted in the labs LAN setup are DE1 SoC and then it use the correct family filter. So if you choose a different filter, then the pin configurations will be different, then the code won't work as expected, and then it won't get implemented also properly, right? We have to be very careful. Just close this reference, and we need to copy this board settings. FICSEMA5. 5C means it is Cyclone 5 device. Okay, we can copy this from here, and then we paste it in the name filter. So that once you paste it, you can get the corresponding device here, 5CSEMA5, right? F31C6. Okay, so once you do this, say next. EDA tool settings, nothing is required. Say next now, and then finish. Okay, now you have the project ready. So what we did is we created a new project, but that project is for the Cyclone 5 device. Okay, that is the Verilog code. That also you don't need to type from your side. Okay, it is available here, which you can directly copy paste. Okay, now if you need to open the Verilog code, it is available in this tab, which I will show you. So you can see the switch to LED. Creating a new file, we should click the Verilog HDL file. So this step you may be aware. But now what we are going to do is, like, we should copy this code. Like you can see, switch to LED.v. Just click that. It will allow you to open it. You can copy this from here. Okay. Now what we can do, you can go to the Quartus Prime Design Software, File, New, Verilog HDL file, say OK, and then you paste it. What is the objective of this code? If you see, there are 10 switches, and then there are 10 LEDs. Whichever switch you are changing, corresponding LED is glowing or not, we are going to check. That's what is the objective of this code. So we will just change the switch, and which switch we are changing, that corresponding LED is glowing or not, we are going to check it right now. Okay, so now you can say file, save as, switch to LED dot, that you can save. Okay, what is the logic we did now? We have opened in the lab manual. You can see here also the code is there. Module switch to LED. So don't try to copy this. If you try to copy this and paste it, what will happen is there may be extra characters, right? Because you are trying to copy that from the PDF. There are chances that some other extra characters can also be copy pasted. So it will be a trouble for you. So it is better to click from here and then you copy paste the code. Okay, right. That's what is explained here. Make sure carriage returns and new lines are in the right location or your code will not compile properly. Please ensure that you do it correctly. Right. First, what we will do, we will perform first analysis and elaboration. Okay, just click here, analysis and elaboration. So when you perform analysis and elaboration, it shows that there are 0 errors under the code. Okay, so that means there is no problem with analysis of this code. Right. Now, what is the challenge portion that I will explain to you right now? When you open the lab manual, like the D1 SoC, right? Lab manual, if you have a look at the user manual here, see, let me close this. Okay. If you open this here, how many switches we want? There are 10 switches we wanted for this design. And how many LED we want? There are 10 LEDs we want. Okay, so all the 10 switches and all the 10 LEDs we wanted to type here. Let us explore that here. Like if you see here, there are 10 switches. Okay. And IO standard is provided here. And then there are 10 LEDs. Okay. Now in the earlier example, what we did is we performed the pin planning manually. When we need to do manually, what is the problem? What is the challenge when you say we have to provide the numbers properly? There are chances that we may type it wrongly, or it can come in the lower case, or you will have issues in editing them, right? Because of that, what is the challenge when you say these 10 switches and 10 LEDs? It will take a lot of time for you in order to type them manually and perform the task. What is the another shortcut we have is called as we have the tickle file, where you can do the pin planning automatically, where you can copy paste all the pin configurations so that it could be automatically taken by the So is that possible when you say yes? That is possible here. We are going to learn that one only in this particular stage. Where is it available? When we open the lab, right? You can see the lab manual itself. Assigning the pins is here. Okay. When you click here, assigning the pins, you can see when you go to the pin planner, it is showing a blank screen where all the locations we have to insert. For example, I open here and then I go to the assignments and then I go to the pin planner. If I open the pin planner here, there are 10 LEDs and then there are 10 switches like inputs. All the 10 switches are inputs and all the 10 LEDs are out, right? So location is completely blank. We have to provide the location right now. So when we start going through the location from the lab manual, right? If you wanted to do this from the lab manual, and then you need to enter this one by one, it will definitely take a lot of time. How are we going to solve this problem? When you say there is a pin planner tickle file which is already available in the lab manual, so that you don't need to do and type it from the lab, from the user guide. Okay, so what you can do here, just click this T1 SoC pins.tcl, say hello. This will take to a page where you have all the information that are required. The last one is a clock pin that is not required for this design because it's a pure combo logic. But since it is given, right, if you are going to do sequential logic later, then you can copy this clock pin also, right? So you can just copy this from here. Go to the Quartus Prime Design software. Okay. Go to View, Utility Windows, and then expand the tickle console. Now in the tickle console, just paste all the commands and then say enter. What we did, View, Utility Windows, tickle console. Once the tickle console opens, what we are supposed to do, whatever tickle commands which we copied from the lab manual, just paste it here. Now you open the pin plug. Here. Whatever we type, right, all these things are available. The locations of all the LEDs and the locations of all the switches are found. So you can see their locations here. Right now, what we can do right now is we can perform synthesis, implementation, and then we can generate the SRAM object file. All the three are possible right now. So what we can do is, like, the easiest step is you can perform compilation at one stretch. So just click here, the play button, and say start compilation. Till this step, it is in your local laptop. We don't require anything. Okay, in your laptop, once the lab manual is shared with you, we can do everything without any issues. Okay. Now, what is the next step we need to do? Is like we have to ensure that we need to implement the design onto the board with the lab LAN setup. That means how the board is hosted and how are we going to achieve that? That I'm going to show you right now. Any questions you have so far? Yes, please let me know. So this is the easy step. This you can do it like any design. You can take it which uses switches and LEDs, and we are going to implement the design onto them. How are we going to implement? Is like the first one is the traditional method where we have the FPGA board already available with us, the physical board which I showed you. The second one that we are going to do with the virtual labs with remote console. Right now you can see that it is compilation is successful. Now you can see everything is done. Right, and what is the time taken? Everything is shown here. Okay, right now open the lab manual. If you see here, all the pin configurations are done, and then we have compiled the design also. Okay, how are we going to program your FPGA design using the labs LAN setup? First thing is we have to open a student account there. Okay, once you click the link, it will take you to the web page. Yeah, yes, sir.
Yeah, sir, I have a question.
Yes, please.
Sir, when we uploaded the tickle file, so it only did the pin configuration, but like when we did the constraint of the AND gate, So we also change the voltage, IO voltages.
Correct. We can do that also. Actually, see here, the main intention was not the voltage, right? So we have to do both. You are right. Okay. The main intention was not the voltage. The intention was how are we trying to access that resource? That's the idea.
Okay.
So it is always better to have everything set up in the tickle script. So we can definitely add those commands because they are available in the Quartus settings file.
Yes,
we can add those values and then we can definitely do that. Yeah, it's a good question, but it is the intent. Since the intention was different, that was not discussed in detail.
Okay, sir. Thank you.
Yeah. Right. Now what we have to do, I will let you know, is we have to open the account, the credential in the LabsLAN setup. Right. Now, what is LabsLAN? First, we will understand that. Then it is easy for you to get into the details. Okay, so just give me 1 minute. I will explain you about LabsLAN setup. Then we can get into the details of how this works out. Okay, right. So I will open the LabsLAN setup details to you. We are very clear till this place, programming your FPGA. But what is important right now is we have to do with live hardware, or else we have to do with LabsLAN. So live hardware is not possible at this junction because I don't have the board, but then you can definitely do that with the LabsLAN setup online. How do we do that? When you say, that's what is explained in this particular session. I will show you about this. What is LabsLAN? LabsLAN connects schools and universities with real laboratories available somewhere else on the internet. So where it is available? It is available right in Spain, in Brazil, in Australia, in US, or somewhere where it is. So they are real laboratories and not simulations. You can see the board virtually on the screen, right? So they are not just simulation. The laboratories are physically there, and the students from these schools and universities access them. So they are physically available. You can see that they are available, and then we are going to access it. So it is a fee-based model, but then for today and tomorrow during these 3 days our training, they are not going to charge you, right? And then this website, like this sign-in, is always temporary. So it would be at any point of time they will remove your login and password. So it is temporary. So please try to work on it. Whenever you have the design, you create it and then implement the design and check the functionality. Right. Now, what are the two modes they have? One is called as the IDE mode. IDE mode means you don't require the software to be installed in your laptop. Everything is available in the cloud. But the problem with this method is whatever debug capabilities they have enabled, only those things could be available to you since you are trying to access through cloud. What we are going to do in our today's lab is the no IDE. What is the advantage of this no IDE mode? When you say we need to install the software locally in our laptop and we complete the process and generate the SRAM object file only for connecting the board, only the implementation on the board, we are trying to use the LabsLAN setup so that all the steps will be done in our laptop. Only for implementation on the board, we are going to connect through this. So this is the easiest way, because in this, all the features which are available in the Quartus Prime design software, we can enable. We wanted to integrate all the IPs. Yes, you can do that and then create a system, everything, and then you are going to implement that. So there is no specific problem when you are facing the no IDE mode, and that is the mode which we are going to use it for today. Okay, in the no IDE mode, that's the logic. The lab which we are going to see today is the switched LED. Other two labs are available in the lab manual. Whenever you are free, you can try that also. So in this lab, what we are going to see is whichever switch we are changing, that corresponding LED is glowing or not, we are going to see. Right, let me open the lab manual here. For example, if you take the specific link from here, here you can see that login as a student. Okay, or you can see that, okay, login as an instructor, like this. You can see that. This is the way where you can get the screen, right? And another important thing is, like when you click this link, It will take to a page where you can install. You can see that. Create a student. You can see you are about to proceed to register in the Intel hardware. However, you are not logged in Labs. Means you can create a student account and then you can log in as a student. If you already have a username and password, you can log in as a student. Otherwise, what we are supposed to do is like we have create one. So definitely you may not have one, right? So then you have to create. Now you can see that once I have created, since I already have a login and a password, it directly takes me to the page where I can access the lab. You can see that Intel DE1 SoC board, and it shows that no ID, because we are going to have the no IDE mode, means we are going to upload only the SRAM object file. All other things are done in our laptop. Access this lab, you click. Okay, then again click access. Once we do this, it is reserving a board for you in order to implement your design. Now you can see that this is present in the University of Washington. And then you can see there are only 10 minutes time. You have to implement a design onto the board. Okay? I will try. If it is not working, then I will connect another network so that it will be faster. Let us try our level bit here. Here you should see this file. Then we should go to the C drive where we have our design. Okay. So logic gate design, not logic gate design. It is like lab slant demo, right? Switch to LED demo. Go ahead into that. Yeah. Inside this, there is an output files folder. Inside that, you have a switch LED.SOM. Say open. It's only 2 minutes now. Upload it. Okay. Let us see how long it takes. Maybe whether we have the success or not. Let us see. Yeah, hope we can reach. Okay, because we have 1 minute time. Sometimes you may not. Okay, in that case, you have to again upload it. Let's hope for the best. Good. We have a minute time now. Okay, so now we have uploaded it. So we have a 1 minute time so that we can check it. Now you can see that there are 10 switches, right? Whichever switch we are changing, that corresponding LED is glowing or not, you can take it here. You can see the board connected here. For example, this switch you change. You can see whichever switch you are changing, that corresponding LED is glowing or not, you can do. See here. Not only that, if you have completed this, right, before 3 minutes, okay, don't log out. Just say leave now. Okay, because if you log out, again, you need to log in. There are chances that you may not get the system again, right? It will take some time for you. So just to say leave now, and then you come to this page. And from here, again, you say access. So that if you have another file, you can try that lab also now with this option. Okay, for example, if it goes inside, right, one more important thing I can show you. Use files when you say, this is your file, which you have created, the SRAM object file. But then there are some demonstration programs that is given by LabSLAT. You can see that blinking LED, mirroring switches, clock, digital trainer. Digital trainer is one where there is an AND gate, OR gate, all the different gates, logic gates are available with the 2 inputs and 3 inputs. And we can check the functionality. All these things are available for you as reference. So if you wanted to try these demonstration programs, yes, you can. You can program into device and then try them. But I have the design already. I wanted to check when you said you have to click here your own programs, and then you have to choose the SRAM object file. So this is called as the remote hub, and this is available at the University of Washington. where you could use our Intel FPGA, which is D1 SoC board, for implementing the digital logic design. Okay, so again, I am saying leave now so that you can come back to this page. Okay, once you log out, then you have to be very, very careful, right? You can see how long it took for logging in and then uploading your SOF file. So you have to be very, very careful with that. Okay. Now, this is explained in the lab manual. So these links, if you click, it will automatically take you to that page so that you can create your own credentials and implement the design onto the board. So as I mentioned here, you can see do not log out of the Labsland window for the duration of the workshop, or your credentials might expire. So you have to be very, very careful, right? It is literally only 2 minutes because the first minute will be going in uploading only. You will have literally 2 minutes for you to complete your lab exercise. So this is the kind of image which you are seeing there. And once you upload your SRAM object file, you can modify the switch and then you can see the corresponding entities. So I have done the first lab for you. I will share the lab manual with you, which has 2 more labs. One is on the 2:1 multiplexer, again a pure combo logic. And the other one is on the Night Rider, which is a clock divider code, where it will utilize the clock. So only difference is instead of the other pin configuration, you should also copy the last tickle command because it uses a clock for the design. This you can practice. Exactly same steps are followed. There are different ways of writing the 2:1 multiplexer. Whichever method you feel comfortable, you can follow that method. So this is for the second lab. And for the third one, Night Rider, which is a simple clock divider. The Verilog code is available here. You can click that code and then get the code. And you can perform download and then take the output here. So this is also possible here for you. So if you want more references, that is available in the lab manual, where you can refer that from the YouTube also. Okay, so I can log out from here because there is no need, right? So you can log out. So you can, once you create, you can get this link. You will have the username and then the password. Okay, you can have your username, so that's not a big deal for us. Right, any questions, sir? So far, anyone have any questions in this? Please let me know.
In the chat window, there is no questions.
All right. So if someone wants to ask questions, yeah, please unmute and ask. This is something which is important. Yeah. Yes.
Sir, is there any limit that the student account can upload 3 times or 5 times in that virtual Labsland, sir?
No, there is no problem. You see, once you log in, you can do 3 or 5 because we have 3 labs, right? So you complete the workshop with 3 labs. Still that you can keep it. The only problem is it will be slowed down because multiple people will try to access the boards, right? So based on your internet connectivity and other things, it will be slowed down. That's all.
Sir, one more question. So if at all, if I want to connect external devices, like, in ADC, we are converting, right, we are using some analog analog component. So is it right possible that we can do that also in Labsland?
Yeah, so the problem is like now at this junction, they have done only with the digital kind of examples. Okay. So there is no external interface examples that are available. That is available in our like traditional setup, but in this setup, it is not available.
Okay, so that means what are the components which are present on that FPGA, we can perform all those things.
Correct. They have an IDE, right? So in that, what is available in the cloud that we can do. But in our non-IDE method, right? So that specific logic is not available.
Okay, fine. Thank you, sir.
Yeah, thank you. Right. So there are 2 more things which I need to explain to you. One is called how do you open an example project, like you have a reference example. And then how do you open a language template? Because when you are not very sure with what to write in Verilog or what to write in the system Verilog or VHDL, but somehow I have to compile and simulate the design. How do we go ahead with say? That is also possible with the Quartus Prime design software, which I explained that to you. Okay. I will share this lab manual because this lab manual, so this folder, which is a zip file, if you open it, you have the DE1 SoC pins.tcl, you have the tickle file, and all the Verilog code, Night Rider, Mux 2:1 in all the 3 methods, and then switch the LED. So all the Verilog codes are available, and then along with the lab manual. So only the lab manual is sufficient for you. You don't require the codes also. If you click the lab manual itself, it will take you to the corresponding Verilog code GitHub site. It will also take you to the tickle file. So you don't require any other extra files. Only once you have the lab manual, that is sufficient. Is that fine? All right. Now let me walk you through the rest of the things. Now, for example, I closed this project. Now I need to create a new project where I'm going to open a template. Means I'm going to use a language template. How that would be possible? Let us see that. Click here, new project Israr. You can provide anything here. For example, I say here C drive and say language template. Okay, something like that you take. And then what is the name? You can say RAM, that's memory, something like that you take. Or you can also take memory. So it is easy for you to remember. Okay, next here. Create it, empty project. Okay. And then say next here. So you can choose any device here. So let me go through the Max 10 again. So 10M50, TAF, 84, C7. I can click that and say next. No EDA tool settings here. So just say something. Now, if you go here, file, new, and say Verilog HDL file, just say OK. Now you can see there is a language template. Insert template will be there. If you click this, okay, this will take you to the insert template launcher. Here you can see timing analyzer, the Verilog, tickle, Verilog HDL, everything is there. Now what you can do is just expand Verilog HDL here. And you can see full designs and then constructs. For example, if you have any doubt only in the constructs, then you can expand that constructs. But if you have any issues on the full designs, like you can click here, full designs, and then RAM and ROM. Okay, I wanted to have the Verilog code of memory, RAM and ROM. Just expand that. I want the Verilog code of single port. Let us click that and say insert. Close. Now what happens? You could see the Verilog code is directly in the logic. Now what you need to do is just change the module name to memory, because whichever name you have provided, that you change. Now you can save it. So you say file, save as, and say memory dot. So what we have done, we have not developed the Verilog code. We inserted the template of the Verilog code directly here. Now we can perform compilation. I just say start compilation here. Now you can see that in the earlier examples, it was not showing anything in the memory resources. It was showing 0. Now you can see the total memory bits 512. You can see that it is also using the memory resource. How many are utilized and how many are available, that also you can see. Right? So we didn't write the Verilog code for this, but what we did is we used the template. So remember, insert template. There you have full designs and you also have the construct. For example, if you have doubt how to write case construct, only case and end case will be there where you can insert it and then you can modify whatever you wanted inside. So that is also possible. Now if I go through the netlist viewers, you can see RTL viewer. You can see the memory here. You can see there is the memory RAM. Right, and if you wanted to see that in the synthesized schematic also, you can see that. You can see that. So this is a block memory, RAM block. You can see that. Okay, right. What is the another one? When you say till now we were doing with empty project, but then if you wanted to do a reference project, so how do you do that? Say, so here you can select the corresponding. I will show it to you right. I'll go close the Epsilon setup. Now you can say dev store for Intel. This is what you should type. Okay. This will take you to the design store. So design store for Intel FPGAs. So exactly you can see FPGA cloud.intel.com. If I take this design store for Intel FPGAs, right, I'm just directly typing in Google so that you should not worry about the link where it is traceable like that. Okay, so it is very easy for you to search and get the details. Okay, now you can see that just which is the design store for Intel FPGAs. It directly takes me to the page where you have the design example, which are already there. You don't need to create anything. For example, the max device I wanted. And you don't bother about the Quartus Prime version. It can be any version. That is not our problem. But I wanted the lab example specifically for one board that you can select here. Max 10 DE10 Lite, because that is the board I have in my hand right now. So can I take one example and then try it when you say yes, that is possible. So you can select the family here. You can provide the development kit details here, and then you can select any of these examples from here. For example, let me explore one and show you. So you can see SDRAM RTL test, Max 10 DE10 Lite is there. I am just clicking this example. And then now you can see that. Okay, so download. You can say just I agree. This is download. Okay, you have the project archive file, which is already there. This we can use it and open it directly. For example, you can close this, close project, and say open project, and go to downloads, and say project archive file. So you unarchive, and then it will open. Now you have the entire Verilog. Okay, since it was generated in 16.1, and we are opening that in 18.1. Since it is like 2 years, right? That means version is different. It is expecting you to upgrade the intellectual properties, all the IPs which are available before we start working on the project. So what you should do is launch IP upgrade tool, we should say, and say perform automatic upgrade. This is very, very important for all the design. Why this is important is because the design file was generated in the previous version, and then we are trying to open that in the newer version so that the IP cores should be compatible to this version. So once it is generated, it will ask you to close. Okay, so then we can continue. Right, you can say close now, then we can continue. Now everything is available with you. For example, if I open the files, I have all the files. We have not generated all these files. They are already available. Okay, so what are the three methods we have seen? One is we can open an existing project that is already available, you know that. Now, in the creation of new projects, one, you can type your own code, or you can insert the template. In the third variant, you can directly go to design store for Intel FPGAs, and we can take the reference design, okay, which is available for the specific family, and that we can download and use it for our design. So all these things are possible. Do you have any doubt till this flow in the Quartus Prime design software? Please let me know. I will share the lab manual with you so that I will share with the professor and he will put that in the shared drive so that you can practice that in detail today. Are there any questions, sir?
Not in the chat window, sir.
Sure, sir. So, yeah, if there are no further questions, then we can wind up for the day. I can share the presentation PDFs and the lab manuals with you, sir, by email. You can share that with all the registered participants and then put that in the share so that they can practice all the labs today.
Yes.
And if they have any doubt, they can approach me tomorrow, sir, during the session.
Yes, no problem. So participants, if there are any specific questions, you can ask now. Otherwise, we are going to finish it a little bit early than scheduled. So are there any questions?
Hello, sir.
Yes.
Yes.
Is it possible to implement the applications like transceiver in the virtual labs?
No, as of now, there is a problem with those kind of high-speed interfaces with PCI Express like that.
Okay.
So I hope that will also be done in the later logic. But now their main interest is on the digital logic design and the SoC.
Okay, sir. Okay, thank you, sir.
I think there are no other questions, sir. So we can stop it here. Thank you.
Thank you, sir. So what I will do, I will share the lab manual and the PDFs with you. You can put them in the share so that they can also practice it, sir.
Yes, yes. Already I have shared the session video, session 1 video. So once this gets ready in my cloud, I will share this also so that they can use step-by-step method to check everything.
So, Suhas sir, I request you to please share all those manuals in the drive, sir, and
Yes,
share
yes,
that.
I'm going to do that. I am going to do that. Okay.
Fine, thank you, sir.
Yeah. Yes, sir. All right, sir. So along with that, I will also share the lab manuals and whatever things I have in my drive so that you can put that across and then they can practice it for the day, sir.
Yes, yes, sir. So thank you very much, everyone. From early morning to almost 1:10. So you have been very attentive. So we'll meet tomorrow sharp at 9:30 once again.
Yes, sir. Yeah, definitely. So if they could practice, then it will be an interactive session for us tomorrow because we need to work on timing analysis, IP, platform designer, introduction to SoC. So many topics are there for tomorrow, sir.
I hope they will practice, sir. That's why I am sharing all the information.
Thank you so much, sir.
Yeah, thank you. Thank you. Have a nice day, everybody.